How many of you have heard of the traveling salesman problem? How many of you have heard of it in a computer science class? Okay, so there's lots of different versions of the traveling salesman problem. And traveling salesman problem. And it's not teaspoon. TSP is traveling salesman problem. It's one of the most common, when you say TSP, people know exactly what you're talking about. So I'm not going to go too much into the theory of levels of difficulty. I've put some links online in the additional comments for today about NP complete, NP hard problems, the difference between P and NP. These are classifications that have been developed by mathematicians and computer scientists to give you a sense of how difficult problems are. And frequently you have a whole class of problems that are similarly difficult. And in some sense, if you can solve one of them, you can solve all of them. What's fascinating about some of these classes is these are classes of problems that are hard to solve, but it's very easy to check and see if a solution is correct. So can anybody think of the classic example of a problem which is hard to solve, or at least we believe it's hard to solve, but it's easy to check and see if you're right? RSA. RSA. So what in particular in RSA?
Well, it's hard to find two numbers that are relatively prime.
No, very easy to find two numbers that are relatively prime. You're close.
It's hard to find two prime factors.
It's hard to factor a number. So, or it's felt factoring thought hard. Multiplication, easy. So hard, I give you P times Q and ask for P and Q. Easy, I give you P and Q and ask for P times Q. Okay? Now, what's so beautiful about this factorization problem is, while it's hard to factor, is it hard to check and see if somebody factored correctly? No. So, factoring thought hard, but it's easy to check. And that's the big difference. So a lot of times, you cannot find a method that will give you the answer very quickly. But if somebody gives you a proposed answer, you can check and see if that's right. And so that is the advantage of these spaces. So it turns out the traveling salesman problem, we can actually check a lot of times and see if a solution is valid without too much work. The difficulty is finding that solution or finding something that's close. It's going to turn out to be an integer linear programming problem. Integer linear programming problems are hard, but we can at least formulate them and set them up without too much difficulty. So I will give you a warning of one problem that is on the midterm. It will be related to something along these lines where you'll be asked to formulate constraints and write something down. It'll be similar to you will be asked to create a tweak and make the problem harder or more interesting. There will be other subsidiary questions related to it. The other hint I will give you on the exam is that at least one question was solved by Kayla. Okay? And she hasn't gone to all the lectures. She's only watched a few on YouTube. Okay? So there will be something similar to this. This is one of the skills I want you to get out of the class, is I want you to get out of this, how do I formulate something? So I will give you an example. If you want, as a practice problem, in addition to the ones we've already done, I have put down the game of Battleship. This is not the game of Battleship from, is it Parker Brothers or Milton? Whichever company, it's not that Battleship that you might have played as a kid where you have two people. It's Battleship with just one person. All right. So how many of you played the one-person Battleship game? It's awesome. So you basically get a grid, and you are told how many ship units are in each row and how many ship units are in each column. And given this information, can you figure things out? Does this seem like any other game you might have seen? It seems a lot like Minesweeper. I'm actually under agreement not to ever play or discuss Minesweeper in great detail, so I can't say more about that. But there's lots of things you can do that are very similar to this. All right? Some of these games can become addictive, okay? And you can play them far too much. Okay? But this is a great practice problem if you want for the exam. So I've posted a link to it in the additional comments. Look at it and try to write down how you would do the Battleship game. There's going to be a special review session this Sunday from 5 to 8 in Bronfman 103. Okay, so the traveling salesman problem. You have C cities, say 1, 2, ... C. And at city I can go to, we'll call it maybe S sub I. And this is where the notation gets horrible. C sub I1 ... C sub I sub R sub I. This is where tech beats Microsoft Word in terms of all the subscripts on subscripts. What would be the simplest assumption to make, or the simplest assumptions to make about your cities? They're equidistant. That would be nice.
SI equals C for all.
One of them is SI equals C, that any city is accessible from any other city. Now, unfortunately, the more accessibility you have, the harder the problem is, because you have the ability of going in many different routes. Another thing might be to assume that you only have a certain number of cities accessible from any given city. So depending on what constraints you put in here, the problem can become very different in terms of the complexity. Maybe each city only has 2 cities that's connected to. Right? I'll leave you to think about whether or not that's a difficult problem if each city only has 2 neighbors. Okay? The more neighbors you have, the harder it becomes. So if each city is always accessible, how many paths do we have? You know, we want to, the traveling system is we want to visit each city once and only once. So visit each city once and only once. Yes? It would be n factorial. And that's approximately n over e to the n square root of 2 pi n, to just give you a sense of how big it is. I'm sorry, n factorial. Oh, sorry. Sorry, n is c. So we'll do c. Well, actually, here, let's say that the last city is city n. And then that way I can use little c as a subscript. So we have n cities. There's n choices for which city we start with, n minus 1 choices for the next city, n minus 2 for the one after that. Yeah, in fact, that's why it's kind of nice to use the letter n here. C represents an arbitrary element of C. And the difficulty is I've got to say which ones do I have. I don't necessarily know which cities are available. When you're writing solutions, when you're writing linear code with something like this, I'm quite happy for you to just create a set like this and say, I'm going to sum over all C and S sub I. You don't have to explicitly write down what it is. When you did the Sudoku problem, you might want to break things up. One of them might be a row, another one might be a column, another one might be a block. Well, rows and columns are fairly easy. You don't necessarily need to introduce new notation, but you might want to do B1, B2, B3, B4, etc. for the different blocks. Okay, so now each city is always accessible, so the number of places to go, the number of possible routes, is astronomically growing with n. So if you think of n as around 10, well, we're dividing by e, so it's not so bad, but by the time n is 20, this is beyond 10 to the 10. The number of possibilities is just very large. In a lot of industrial applications, we have 10,000, 100,000. And so there's a huge industry to see how far you can go. Can anybody think of an application of why you might want to solve the traveling salesman problem?
Besides if you're a traveling salesman?
Nope. Not besides that.
Well, if you're a traveling salesman.
So one is if you're a traveling salesman, okay? So the first is the most basic. The reason you might want to solve the traveling salesman problem is you want to have the most efficient route. Another thing is instead of having a route for a traveling salesman, you might have a route for resupply. You might have a warehouse and you might need to get resources to different places. Another nice example is creating chips. Not potato chips, but actually chips for computers in terms of where things are being done. And you want to have the route of least time for moving your laser or whatever's burning the various things. There are lots of situations where you want to find the most efficient way through things like this. Another thing related to this is, I think they give the example of like a sheet, and you're cutting the sheet in different ways to make different things. Where are you making your cut lines? Because you have to have a certain number of shapes. Another possibility related to this is scheduling times. Different jobs take different amounts of time. Which jobs do you want to schedule based on how well things can be processed? Lots of things can be converted to the traveling salesman problem. So my goal for today's lecture is to just introduce you to the subject. I'm going to put a couple of papers online so that if you want to read more about any of this, if you want to see some of the techniques, you can do that. But I'm not going to require you to do this. I'm just putting that out there. I'm happy to discuss it with you in greater detail. Right now, this is a practice for the midterm. I'm deliberately giving you something that you have not thought about. I debated having you read about the traveling salesman problem before class. This is a way for you to think live, how would you do on a problem on the midterm? And if you feel right now that you're doing this without too much trouble, then you're in great shape and you're ready for the midterm. If right now this is completely Greek to you, it's either my handwriting is really bad, which is a possibility, or you have some trouble with the basics of linear programming, and we should definitely meet either ourselves, meet with your classmates, meet with the TA, and prepare a little bit more. All right. Are there any other constraints we want to go through? We have C cities. At city I can only go to this. As we said over here, visit each city exactly once. And what is our goal? Minimize something. So it could be cost or it could be travel time. We will minimize travel time. Minimize distance. Okay? This is not necessarily the same as minimizing cost. It could be expensive to take certain routes, but the distance might be small. All right. For now, we're not going to worry about something like that. Could you think of any other objectives you want? Well, if we have two objectives, how could we handle something like that? Multi-objective linear programming. So what's nice is if you have a couple of things that you want to do simultaneously, you can put in some weights as to how much one matters to you relative to another, and this already falls in the framework of what we've done. So the question becomes now, how do we handle something like this? How do we formulate this? So we have to decide what are our constraints, what are our parameters, what are our variables. So need to find parameters, variables, constraints, and I guess the objective function that we're trying to maximize or minimize. So what do you think our variables should be? There's lots of ways to formulate this. Yes?
Maybe the edges.
I'm sorry?
The edges, each edge be a variable.
So that's one possibility. So, we have some kind of network like this. So maybe something like this. So you want to. So your variables would be this edge. So is this edge used in your trip or not? Can you use the edge more than once?
No.
So how will you take into account that you can only use the edge once and only once?
Binary. Did you make it?
So tell me explicitly what your variable is going to be.
It's going to be either 0 or 1.
That's the values of your variable. What would your variable be?
If you've traveled the edge or not.
Okay. But okay, and so how am I going to tell if I traveled? I'll need some other variables.
Do you have two variables for each edge, one being whether it's supposed to be traveled on it, and the other one being the length of the edge?
Well, the length of the edge is an input. Right? We know ahead of time, we'll assume where the cities are. So the lengths we don't actually have to worry about. But you have to be a little bit more careful than just maybe if you have the edge.
I was going to say something like x, I, j, n. So it will equal 1 if the edge from I to j is step n on your journey.
Okay. I think that's a good way to handle it. One of the things we have to be careful about is which direction are we traveling the edge.
I was thinking that if you're going from point A to point B, your goal is to minimize distance. You could use like the shortest path algorithm.
Well, right now I want to just write down my constraints, my variables, my parameters. So what are you saying I should use for my variable? So we've got two suggestions. One was to use some kind of, very similar to the scheduling problems. You depart city I for city j at time n. Another possibility was to say whether or not this edge is used or not. The difficulty with the way you phrased it is I don't know which direction it's been used. And at the end of the day, I've got to piece everything together and say, have I gone through the path? Have I hit every city? So I'm not saying that it can't be done your way. I'm saying I prefer the scheduling like an airline. It is at a certain time I'm departing. And then do you have a suggestion for another way to, because there's lots of ways to formulate this.
I was just thinking, if your goal is to minimize the distance and if it's like a 4-point system like this, then you can just use like the shortest path algorithm.
Well, right now, I don't want you to say something like the shortest path algorithm. I want you to tell me what you will use as your variables. I want to set this up as a linear programming problem.
Why can we only travel each path once?
Because the paths are connecting the cities, and we don't want to revisit a city.
Right, but it seems like there'd be a scenario where you have to.
So there is that possibility, and that is a generalization, where it might actually be better for you to revisit a city. And in fact, if I give you something absurd,
Are we assuming that we can do this without visiting the city twice?
so there may not be a solution to the traveling salesman problem as formulated. So if I give you this, is it possible to visit every city once and only once and hit every city? No. So in this case, there would be no solution to the original TSP. So your suggestion, because if I start over here, as soon as I get down here, I've got to come back up. If I swing over like this, I've missed these points. So I can't start off in through here. By symmetry, can't start on any of the other ones. So I guess to make the argument even easier, I should have the same number of dots in all of them, so it's completely symmetric. And so by handling this branch and showing this doesn't work, I now just have to handle this branch, which is even worse. So in this configuration, there is no solution to the original traveling salesman problem. So what you might have to do is you might have to then say, I am willing to allow myself to visit some cities multiple times. And in fact, if you only care about the cost, would you be willing to do that at some point? Yes. So what you would then do is the following. I can visit here to here directly. And I'll just view this path as a connection like that. And the cost of that will just be the sum of those two costs. And I will just pretend that I haven't been in there. If you do that, you now have the complete graph in some sense. And that makes things a lot harder. You have a lot more things to look at, a lot more possibilities. So depending on how you formulate the problem, it can greatly change whether or not there is a solution and how hard it is to find that solution. So we will stay for now with the original formulation. You cannot visit a city multiple times. Once you've seen Cleveland, there's no reason to go back, right? I'm sorry? All right, all right, so now I like the idea of choosing as the decision variable as xtij, which is 1 at time t, leave city I for city j and 0 otherwise. I think this is a very nice way to formulate what's going on. How long is it going to take us if there is a solution to travel the whole network?
Like how many steps?
How many steps?
However many cities there are.
However many cities there are minus 1. So travel time is n minus 1. Yes?
We're assuming the cities are equally spaced.
No. Where did that assumption come in?
He's assuming each.
We'll say travel steps. You're right. You're right. You're right. Steps is a better word than time. Is that what we care about is where's our first step, where's our second step, where's our third step. And so we don't care how long that is. We just care where we are at a given step. Yes?
We want to set xtij equals to xtji to account for the idea of going the other way.
No, because it matters which way you go through. Flying from Boston to Cleveland is not the same as flying from Cleveland to Boston. And in fact, you could even have different travel costs going in different directions. The distances could be different. You could have certain one-way roads that may not be accessible. You often assume a symmetric version of the problem, and anytime you can have any simplification, that will help with the runtime. But there is, if we are flying from Boston to Cleveland, that's not the same as Cleveland to Boston. What's nice about doing things in this, whenever you have this kind of scheduling, whenever you have this kind of movement, is you know exactly where you are at a given time. And you know exactly where you're allowed to go at the next stage. We know which steps, which cities are accessible. Now there's some difficulties. We don't know where we start. Right? If you have to start at company headquarters, and if you have to end at either company headquarters or the West Coast branch, that's a lot easier. Right now, we don't know where we start. So there's a lot of different ways to try to handle this. Because there's a little bit of an asymmetry in terms of where you start, you never travel to it. What's true about every other city other than the starting city? You enter it and you... Well, do you enter and leave every city? No. Not the last one. So the last city and the first city are a little bit special. Every other city you enter exactly once, and you leave exactly once. So you have lots of different ways of trying to figure out how you want to write down the constraints. So one way you could do it is, what if you phrased your constraint, I know which is my starting city and which is my ending city. And for each one of these, I looked at all my choices of my random variables so that each city is entered once and each city is left once. If I can find a way to do that, do I have a valid path? So, except for first and last, each city entered exactly once and left exactly once. Would that work?
Like, do we need the constraint that, do we need a special constraint for our last city?
Well, I'm saying, I seem to interpret people as saying that this was a possible approach. That except for the first and the last city, every city is entered once and every city is left once. Is this sufficient or is this not sufficient?
Well, if we're still doing it like by the edges, I'm not sure if like, so say you took.
So I think we're doing it this way with like a departure.
Yeah.
Doing it more from the vertices.
Yeah. Okay. Yeah. That's what I was concerned about, the edges thing.
Right.
Come in and, yeah.
But is this concerning?
Well, if you enter at time t, you have to leave at time t plus 1.
So we do want that as well. So one problem with this is that we could have a schedule that's valid with lots of hopping back and forth like this in terms of how we're traveling. And so in something like this, one issue is might have hops. If you enter a city at time t, you leave the city at time t plus 1. Unless, of course, it's your final city. Any other issues with something like this? There's at least one other issue.
We don't know if the leg is a legitimate path, or you'd have to add a constraint saying that when you go from one city to another, that's a valid way to go, or unless we're assuming that already.
So so we need to make sure that they're valid movements. And so this is a condition that's definitely true. Every city, except for the first and last, is entered and left exactly once. But this is not enough to capture the entire complexity of the problem. So if you tried to capture the problem just using this, you would capture a lot of it. But there would be many things that you would miss, and you would have to find constraints for that. The other thing is there are some dangerous configurations. What if you had the following? Here's my starting city. I travel to here, and then here's my hop. I go around in this cycle, then I hop back and I go here. This is a very bad way to have the hops going on. That satisfies, except for the first and the last, each city is entered and left exactly once. And this just shows you a real danger of the hopping.
Wouldn't the last city in the starting line of 3 not have been left?
That way
You entered twice.
Okay, so good. So maybe this is not a problem because of how we're defining things.
Yeah.
It's somehow we now just entered over here. Okay, so maybe this might be okay.
I think it depends, like, how are we thinking of a hop?
This is how we're thinking of a hop.
Is a hop, is a hop we can leave a city having not entered it?
Right,
In which case it would be taken care of by that constraint.
right. Yes.
You just, like, our notation is a little different on, like, the right and left, but if, like, say, x, just like ij has to be an element of si, and like, rephrase si, so it's like, these are possible paths, and it just has to be an element of one of those, like, ignoring the t part.
Right, so I think if we start expanding along these lines, I think this is not a bad way to start. But I think we do need a little bit more than just this condition. I think it's a very good way to start. But this is what I want to discuss with you as to how easy it is to suddenly be assuming something. This is definitely a condition that is satisfied by the solution, but it's not enough to guarantee the solution. So one thing is to treat the first and the last cities a little bit special. Sometimes it's useful to have time -1. So you start at time 0. Maybe at time -1, I start myself at another city, and I travel to my initial city. And I don't really care in terms of checking to make sure that I've never hit a city twice. Maybe I don't care where I was at time -1. And similarly, I don't care necessarily what's going on at the very end. So one constraint, so for all t in 0 to n-1, or maybe n-2, if x t I j equals 1. So this means at time t, I have gone from city I to city j. What must be true? xtji is 0, yes. But more than that.
xt everything is 0.
So one of the things we know, we would know that all the other, if we travel here, we know all these other ones. So in fact, that might be a better constraint to just put the sum over all I, the sum over all j of xijt, I'm sorry, xtij is at most 1. We can just put that as a very basic constraint. And this will tell us that at any moment in time, you enter at most one city from at most one city. We can also put on some silly constraints, maybe such as the sum of xtii equals 0. What does that mean?
Never go from a city to itself.
Right. It might actually, and I had some students looking at this in an independent study last year, you might actually want to allow yourself to travel from where you are to where you are. What that might mean is if you're traveling and trying to visit many different cities, it might make sense in terms of cost to spend a few days in one place. Maybe you actually want to do something in these cities, or maybe you need to wait for the airfare to go down, you want that Saturday stay.
I was just saying you also want to say that XTJI is 0 for like all time after like you propose that.
Oh, that you never come back?
We go backwards. So that's what I was a little concerned about over there. That if you said
Right.
IJ is 1, there's nothing there that says that JI can't be 1 at some other time.
Good. So another constraint we could put up here is the sum over all t, the sum over all I of xtij. What should that equal? So does that tell me that I always enter each city exactly once? You give me a city j, so no matter what j, this is for all j, t goes from -1 to n-2. Each city entered exactly once. Yes?
You also
Wait, before we go on, I just want to make sure, did this code your constraint?
I think so.
So you give me a city. Let's fix the city j. I've got to enter it at some point. How do I enter it? There's got to be some other city I that I come to.
Yeah.
And so we've got to be very careful because we have that initial starting city. And that's why I think it's really nice to have this time -1. At time -1, I start somewhere and I come to my initial city. Now, if not all cities are accessible from all cities, that would actually give you some issues in terms of whether or not things are accessible. And so you have to maybe tweak that a little bit. But right now, you give me a city, and then there's some time when I traveled to it. And I never traveled to it twice. Okay, and then this one over here is for every time. If we're at city I, we travel on to city j. So should that be less than or equal to 1, or should we do better than less than or equal to 1? It should be equal to 1. We go somewhere. So fix t in -1 to n-2. We go somewhere. No matter where you are at time t, you're at some city I. There's going to be some other city j that you're going to.
Why does t go from -1 to n-2?
Or is it n-1?
-1 because that'll give you a total of n-1 steps, and it takes n-1 steps to hit n cities. So it's
Okay.
n step.
At the beginning, to enter the first city.
Right. Yes. So we've got,
I think n-2 is right though.
No, because the first city that corresponds to
Right.
the beginning one from t-1 isn't one that we're counting.
The -1 to 0 is imaginary.
Yeah, but still, so -1 to n-1 is n+1 steps. It's just n.
no, because you have 0 to n-1 is n steps with negative.
n+1 steps.
Right. So if we go to n-2,
That's the one thing, yeah.
there's n steps.
So it should be n-2.
If we have an n-1, we're looking at how many times we are entering. And so we have to enter n cities. So we need a set that has size n. So I do think it should be n-2. And this will now give us that we've entered every city. So yes?
Do we need the sort of opposite of that, saying that you have to leave every city, so it's similar to that constraint? Is that
So here's the question. Do we need that explicitly, or do we already have that? See, what we don't have right now is if we enter a city, we then leave that city for the next step. This is telling us every city is hit. And this is telling us for all j, each city is entered exactly once. But right now, if we just had these two constraints, I think we could have something with hopping maybe, depending on how things are defined. So this is a real question, is do we have enough conditions here or do we need an additional condition?
We need like for if xtij equals 1, then sum for x plus 1 j k equals 1.
And so here we will sum, actually we just need one sum.
Yeah, just need a single sum over
Sum over k x t plus 1 j k equals 1. So if at time t we've entered city j, then at time t plus 1 we have to enter one of the cities that's accessible. So this would be k in restricted to just s sub j, to the cities that are accessible from city j. Do I want this for each individual I, or could I sum over all I? Do I care how I entered city j?
Sum over all.
I'm sorry? I think we could just put over here a sum over all I.
So for encoding that if then, you could probably do something like for all I, or xij plus xjk, or xijt plus xjkt plus 1 is less than or equal to an indicator.
I mean, this is going to be impossible to do, I think, if we just speak it.
Okay.
Can you say in words?
Sure. You want to encode whether or not a path from j to k is valid
Right.
into that if-then statement. Or
Right.
I'm
Well,
trying to think of-
here, we're
Yeah.
getting short on time, so let's summarize and let's see if this makes everything. So this constraint over here, for all j, each city is entered exactly once. At every point in time before the end, we go somewhere. And then over here, if we enter city j, then we leave city j for one of the places that's accessible to it. So this constraint would have to be true for all j, for all t from, I think, -1 to n minus 2. So whenever you have constraints, you need to be very clear as to where do they hold. What are you summing over, and what is free? And so here, I need a constraint like this at every moment in time, at every step. I think this might be it. We have our binary variables, and now we have a valid path. We have a path of the right length. So notice it was a huge saving knowing exactly how many steps it took to go through the network. We have n cities, it takes n minus 1 steps. There may be slightly different ways to formulate this, but this gives a rough sense of what's going on. Each city is entered exactly once. That's great. That means we've hit every city. Each city, at every point in time, we go somewhere unless we're at the very end, so we don't stay where we are. And we make sure that whenever we go someplace that's valid. So since each city is entered only once, we start here. Let's say we go someplace. Now we're here. We go someplace else. It can't be a place we've already gone, so we have to go to some new place. We go to some place. It's got to be a place we haven't gone before. Can we ever hit a place we've gone? No. So I think these three constraints capture the entire traveling salesman problem. Yes?
But when I'm just trying to think, like, since we're starting it sort of like with the imaginary travel step, doesn't
Right.
that cause problems with this where now we won't revisit it?
no.
No, because we've now summed over here. So we actually have taken into account entering that imaginary city. You have to tweak the conditions a little bit because of the first and the last one. And so this is one of the things that's a little bit annoying. So here, every city is entered exactly once. Yes?
It becomes easier when you actually program the test.
In what sense?
Because like a way of coding it would be to just choose one of the cities and then look at all the possibilities from that city to another city. And so you already have your first one and don't really if you have the constraints such that they're imposed on the remaining cities, it's easier to program.
So what you're saying is you start off at some city, and then you look and see which cities are available, but then how do you choose which one you go to?
I would try them all.
Well, if you try them all, you're at the level of n factorial.
What if we want to go home afterwards?
Why?
Retire.
So you can always then put in a constraint such as your final city has to be your home city.
Right, that'd be cleaner.
And that would be much cleaner.
Isn't the point of this problem that we're going to be as slow as n factorial though? Isn't
No. No, the point is that there are faster ways to do this. One thing you could do is if you want, you could have a start city which is accessible to everyone, and you could have an end city which is also accessible to everyone. And you know what the cost is to travel from the start city to any city? 0. And what's the cost to travel to the end city? So if you do that, you can clean up your constraints a lot. So in terms of how you do stuff like this, if you put in additional things that you don't care about, it can often make things a lot nicer. So you can have this extra minus step where you come in. Really the way we should do this is we should create, I don't know, the Emerald City, I don't know, something really nice where there is no cost to leave the Emerald City to get anywhere.
We could even make the imaginary city the same city.
You could even make it the same city if you want. But I'd like the Emerald City and the Jaded City. Sorry, the Jade City, sorry. Yes?
Could we eventually go through this like in the class where we can go from this to actually putting into a program?
Right, so in next week, I hope somebody's going to help me come up with which environment do we want to learn for this class. And then we'll actually code this. And we'll code the diet problem. So I want you to all have, when you finish the semester, the skills of coding something. So you should be able to code the diet problem. You should be able to code the traveling salesman problem. I think cities between 10 and 40, you should be able to do without too much trouble on computers. Beyond that, it becomes very hard. So there's, I'll give you some surveys as to exactly what can be done. There are some traveling salesman routes of, I think, 100,000 cities that have been solved.
At what point here are we being faster than in our, like, we haven't actually gotten to any sort of savings versus like, are we still in our current?
Right now, this is just setting it up as a program. This is just setting it up in the confines of linear programming. We haven't done any analysis yet. So what I'm going to do is, because this took a little bit longer than expected, I'm going to save the analysis. I chose 2 different methods to look at. I chose the greedy algorithm and the insertion algorithm. These are not linear programming approaches, but these are 2 standard approaches to solving traveling salesman type problems. And so on Wednesday's class, we will go through and we'll see how long would it take to solve the problem using these. Now, unfortunately, when I say solve, it does not mean come up with the optimal solution. It means terminate. And so we'll see that these are both polynomial algorithms. So they're much, much faster than the n factorial, but they're not guaranteed to give us the right answer. The purpose of today was to see that something like the traveling salesman problem can be set up as a linear programming problem. Is this a complicated linear programming problem? No. We still have half a minute, right? We have time to sum up. It's not a complicated linear programming problem. It's essentially 3 conditions, maybe a little bit of tweaks to add the special city at the beginning and the special city at the end. This is not a hard thing to code. To actually have the code run in a reasonable amount of time, completely different. And that's one of the difficulties of integer linear programming. We don't know a fast way to do it. If it's real variables, we can do it very quickly. The simplex method runs in great detail. All right, so what we'll do is on Monday, we will have the lecture at the Art Museum, and I will give you some other stuff to view online. On Wednesday, hopefully somebody will help me doing the coding, or if not, we'll do the coding on Friday. We'll talk about greedy algorithm and the insertion algorithm, and then we'll move to doing something more theoretical. We will do fixed point theorems. And so in fixed point theorems, there have been a request to bump up the level of rigor in this class, so I will now prove the fixed point theorems in full detail. Okay, I will try to do this so that you can't see the finger for once.